So when I wrote the abstract, for those who have read it, I was planning for a 30-minute talk, but it is an hour, which means I have been able to, I'm putting in background, which I think is quite important. All right, so I'm going to tell you a story. I'll get to the cold moving velocity, but after a long introduction, which is about half an hour, I'll be there. Okay, yeah, so I'm going to give you, start out with some thermodynamics. I mean, just mentioning the name. And I'm going to demonstrate that there are another example of a non-thermal thermodynamics out there, which means that you can use the machinery of thermodynamics, but it has nothing to do with classic thermodynamics. And classic thermodynamics is, of course, developed and in the wake of the steam engine. And actually, when you look very carefully, you don't have to actually look very carefully, you'll see that, the steam engine lurks behind everything. I mean, the way the laws of thermodynamics have been formulated is really for the use of the steam engine. Well, here you have percolation theory as another example of a non-thermal. That's an example of non-thermal thermodynamics. There's nothing to do with temperature and so forth, but it has all the machinery of thermodynamics in place. Another example that I know is the non-thermal, the jammed granular packings, the thermodynamics of jammed granular packings. That's Sam Edwards, published in 1989, and which has been running now for 30 years. And Don Frenkel managed to demonstrate that the entropy in that case, which is a number of ways you can pack sand in a box, is actually extensive. It was quite a piece of work. And what I'm going to give you now is a third example, namely immiscible two-phase flow in porous medium. All right, so here's the problem. That's the system you're going to have in mind. And this is worked by Marcel Moura. So it consists of these two plates, glass plates, parallel glass plates. And well, actually, this one here is not glass plates. This is 3D printed. So it's a two-dimensional porous medium with this kind of matrix here. And what you see here, I am sending in here a mixture of two types of liquids, a black liquid and a white liquid. They do not mix. And what you see here, over here, is steady state here. So if you look at this region here, you will see that the averages, microscopic averages, remain constant or they fluctuate about well-defined averages. So this is the system. Now here's a big version of the same system. Namely, this is, again, a Henschel cell. There are these beads inside here that makes up the porous medium. And you send in a mixture of two liquids here, which are immiscible. They flow in here, they mix. And inside here, you have a steady state. I remember now in physics, people were very, very excited about injection of one liquid into another one, and you get these wonderful fractals, etc. But that's transient, and that's much more difficult actually to analyze this kind of steady state. I mean, it's no wonder that people still have problems with non-equilibrium thermodynamics, but equilibrium thermodynamics is fine. It's a much easier problem, but it's been much, much less studied. All right, so this is what it looks like when you are sending in these two liquids. So you have the system filled with the dark liquid here, and you send in at these injection points here, alternatively, one liquid and another liquid. In this case here is air, and this is a glycerol water mixture. So you start out like this. Here's after a while, and here it has reached steady state. And this is what you're going to think about. All right, so here is, what I want to do now is to try to scale up the problem, because when people think about porous media, you're very much into what's happening at the pore level. But there is a continuum level where you're looking at scales so large that actually the pores are so tiny you can forget about it. You can treat everything as a continuum. And the first person who did that was Henri in 1856. He wrote down this kind of equation, where he had an extensive version of it, showing that the flow rate is proportional to the pressure drop, and the proportionality factor here contains the permeability of the porous medium. That is a reflection of the structure of the porous medium. And then you have the porosity. The porosity you put here just to get this to be the average velocity in the pores. It's just something else to do with time scale. And this is the viscosity of the liquid you're sending in. So this wonderful thing is that this K over phi, that's the porous medium. And here's the liquid. That's this thing here. And that is the entire mobility. So pressure drop gives a velocity in that direction. Now, in 1936, Wyckoff and Botset generalized the Darcy equation to deal with a mixture of two liquids, immiscible liquids. And the idea they had was that, okay, so here are the two liquids, they're going in there at the same time. And let's say you are liquid number one. What are you going to see? Well, you're going to see the porous matrix, and you're going to see the other liquid, and they're both going to hinder you, which means that effectively the permeability you see is not the original permeability, but they've been scaled down by a factor, and that factor is this here. This is the relative permeability of the wetting liquid. W stands for wetting, and I have to just correct by, this is the saturation. That's what percentage of the porous volume is actually filled with that liquid. Let's just get this to be the average pore velocity. So you have two equations now, one for each of the two liquids, and they are just basically Darcy equation times 2, one for each liquid. And it is basically that one liquid is seeing the other liquid and the matrix as the effective porous medium. All right, and here comes a important assumption they make, namely that this relative permeability only depends on the saturation, what percentage there is of, in this case, the wetting liquid. Here's how we define it. So this is the physics you put into it. Otherwise, this would be, it's just a reformulation of things. So doesn't really say much, but now you made a physical statement. But these equations here cannot handle imbibition. Imbibition means if you take the porous medium, a piece of sugar, for example, dip it into milk, you see the milk rises into the porous medium. It cannot handle these equations. So you need something in addition. You have to get the capillary forces explicitly in. And you go back to this classic experiment. And here's, the water here rises up in the column because there is now a pressure here, a capillary pressure that is, because of the curvature of the surface, is pulling up. And here's the pressure in the water here. And here's the pressure in the air outside, the non-wetting on the outside. And so the pressure here plus the pressure in the capillary pressure is equal to the one on top. And that's what I've written here. And what you then do is you say, okay, so the two pressures here, think now of both liquids actually percolating at the same time. Then you have one pressure in the wetting liquid and one pressure in the non-wetting liquid. And the interfaces between them. And that interface has a capillary pressure, so you call that the capillary pressure. And you make it into a function of the saturation. That's a giant leap. And it's not very well defined. People hate it, but people will use it. But this is it. This is relative permeability theory. That is used in every single calculation that has to do with how immiscible fluids flow in porous media in industrial connections. Right. So what do these relative permeabilities look like? Well, here is for a North Sea sandstone, and these are liquids with different wetting angle between them. You know, we have a surface here, you have a liquid, one liquid here, the other liquid here, and there's an interface, and the wetting angle has to do with this interface here. So you change that angle, and this is what these curves look like. All right, so now you can go out there and be reservoir engineers, because this is the whole story. One important thing I want to use later on is that if you're dealing with steady state flow, part of that definition is that there are no macroscopic saturation gradients. And the flow here, you will not have a flow going on, you know, like this or this. You will go, on average, everything is going to go in this direction here. Not at the pore level, but macroscopically. And that means that the macroscopic pressure gradient is going to be constant throughout the system. That's a steady state. And if this is equal to that, well, the capillary pressure is very equal to zero capillary pressure gradient. This is going to be important later on. Anyway, so how on earth can one make this into a give a thermodynamic description of this, a non-thermodynamic description? Well, let's start with the statistical mechanics. And here's once again the steady state. Macroscopic parameters have well-defined averages. But of course, this is a driven system. The moment you turn off the pumps, everything stops. And that means that there's viscous dissipation all the time. Entropy is being generated. You're turning flow into heat. So it looks impossible to do an equilibrium statistical mechanics here. But now look at how one deals with equilibrium statistical mechanics. Here's the gas in 2 dimensions. And because this is an equilibrium, and the definition of equilibrium here is that you're not generating entropy. And what does that mean? Well, it means if I take pictures of this gas, stack of pictures, one after the other, and I shuffle them, and then I ask you, can you put them back in order? You won't be able to do it. You're not changing the statistical distributions. That is equilibrium. So how on earth can I compare this here, which is not an equilibrium, this is a driven system. This is equilibrium. How can I make a mapping from here to here? Well, it is possible to do that. And this is the way to do it. Well, you start with the gas in 2 dimensions. This is what I just showed you. These are now particles that are bouncing around. Here I draw the space-time diagram for them. So each particle here is tracing out a world line. So it's kind of the spaghetti here. Now take a core sample and inject 2 liquids and let them flow through like this. Here are cuts through this sample. The gray here is a matrix, and you have a white liquid and a black liquid. And think of this here, this picture here. That's just like this picture here. Think of, this is now I put in a time axis. What if I treat this as a time axis, the flow direction? And to make it even more clear, this is from Journal of Fluid Mechanics. These are the streamlines of liquids in a porous medium. Here you see the porous medium just is cut here, otherwise it's invisible. But look at that, the comparison here. And the key concept now I'm going to use is Shannon entropy associated with the information entropy sitting here. And steady state, no production of Shannon entropy in the slices. You will not be able to say which one came before another one here. There is no production of Shannon entropy in this system. Yes, there is production of molecular entropy because you're turning a mechanical motion into heat. But this coarse-grained level, there is no production of this kind of entropy. So that you can actually use now. We have everything in place to actually construct the statistical mechanics. So here's a porous sample. Here's the time axis, that's the z-axis, that's the flow direction. I have two liquids here, and they are then mixed inside here, and I make a cut like this. The fluid configurations in the plane are in equilibrium in the sense that I won't be able to see which comes forwards. And also in this sample here, look, the total flow rate is constant. It's a constant motion along the time axis. This is just like an internal energy in a closed system. All of this gives us an equilibrium statistical mechanics. Now, if you were to do the traditional way of getting further now, you would think of go into the microscopic equations of motion and try to deliver or construct a what's it called again? Liouville theorem. I tried for a summer and I can't do it. Cannot do it. But you'll have to do it because in the 1950s, Jaynes developed a generalized statistical mechanics based on the information theory. He was trying to develop actually a theory for non-equilibrium thermodynamics. That was his end goal. But he really couldn't do that. But he got everything in place otherwise. And that's what I'm using. So here's the porous plug again. And I take out the representative elementary area, not volume, area. And I characterize it by the flow rate through it, by the pore area. That means I'm cutting and making this representative elementary area, and a certain percentage of that area is governed by the pores. That's the pore area. And since there are two liquids here, part of that area has been covered by the wetting liquid. So you have wetting liquid area, you have the pore area, and you have the flow rate here. And then you maximize the entropy. Right? You can write down the entropy for this, and you maximize it, and you end up with, this is the flow rate for configuration X. X means here how the liquids are distributed and how the matrix looks. This is the pore area for the same configuration. Here is the pore area for the same configuration. Here is the wetting area for the same configuration. And there are three numbers, I believe, namely theta, which looks like it. So we called it agitation temperature, or agitor for short. It's a non-thermal temperature. We didn't want to use the word temperature because then people get, to think that it's temperature, but it's not. Then you have this mu here, which acts as a chemical potential. And then you have another type pressure that's associated with the total area. You can think of this the following way. If I have a porous plug like this and I shrink it like this, that is, I'm then using pressure on the system to change the volume. That's what you would say in classical thermodynamics. So you have these variables, and then suddenly you get all the machinery in place for doing a statistical mechanics, not statistical mechanics, but the thermodynamics for porous media, which is not thermodynamics, it's pseudo thermodynamics because the variables here have nothing to do with thermodynamics, but they just look like it. The same formulas. And for example, so here is the average velocity of the liquids. Here's the agitor, here's the saturation, and I do a Legendre transform. And what do I find on this side here as a sort of free energy? Well, that is actually the velocity of the non-wetting liquid. I put a little hat on it because this is what I would call a thermodynamic velocity. I'll get back to it later on. That's when I introduce the common velocity. But anyway, so then you have the flow derivative as it defined, but you also have that the saturation is the derivative of the non-wetting velocity with respect to this quantity here. You would never have been able to guess something like that. These are the intensive variables, the agitor, the flow derivative, and the flow pressure. That's what we call them because we don't want to use the usual names for them. But they correspond to temperature, chemical potential, and this sort of a pressure.
This is which will vary from the bottom to the top.
Yeah. I have a system here I can slice like this. You know, you can actually construct this. This is not, you know, this way of doing things you could also use for other systems. Further developed turbulence in the channel is actually another example that we're working on. But anyway, so you get these kind of things. You have Maxwell relations. Here's the entropy, here's the saturation, here's the flow derivative, and here's the agitor. So you get these kind of out of the blue type equations. You can control the fluctuations. And let's now spend another 6 minutes on developing now, actually how this pseudo-thermodynamics works. So let's start with the Gibbs relation. And this is what it looks like. Here's the total flow rate through your sample. Here's agitor, here's the entropy, the Shannon entropy. Here's the flow pressure. Here is the area of that, and here is the wetting area. And okay, if I can change the average flow rate by changing the cluster structure. That's this one. When you change the flow rate, you change how the clusters look. That's a change in entropy. So that's this part. This one here is a change in pore area. That's what I said. If I, for example, change the porosity, that's going to affect this here in my representative elementary area. And I can have a change in saturation. So this is the Gibbs relation. So what's heat? Well, think of implementing the porous medium on a torus. Santa Nucinia, I'm a close collaborator in Trondheim. He is, in his models, he's using this kind of donut quite often. And the point now is that if I do the Gibbs relation on this system here, it's a closed system. That means that the saturation is constant, so this is 0, and then don't change the porosity. This is 0. Then the only way I can change the total flow rate is by changing the entropy. And this is heat. I change the pressure, and that changes the way the clusters look, and that's heat. So heat increase in flow rate without change of saturation or pore area. Zeroth law of thermodynamics, well, that is if I have to define a temperature, and in classical temperature definition there of temperature is what you get from a thermometer. That actually isn't the definition, but it's closely related to the third law of thermodynamics. So here's the porous medium. I have one porosity here, and I have another porosity here, or one set of wetting properties here, another here. And I send in two liquids here, different velocity and so forth. They have different agitor, and then I remove this bar here, and then up here they mix, and they end up with the same agitor. That's what you need. But that's exactly what the pressure does. You start up with different pressure gradient here and here, but up here you're going to have the same pressure gradient everywhere, otherwise you'll have cross currents. So actually the pressure gradient acts as an agitometer. Difficult word, it's a thermometer, but it's for agitor. So the agitor is actually a function of the pressure gradient. And the constitutive equation, that's flow rate as a function of pressure gradient, plays a role of an equation of state here. Now, the zeroth law says that if I have three bodies A, B, and C, and if A and B are in equilibrium, I put them together, they don't exchange energy, they have the same temperature. And if A and C also, when put together, do not exchange energy, they have the same temperature, then B and C will also be in equilibrium. So here is my torus again, and I have one property here, one property here, one property here, and what do I see when these things flow? Well, I can never get a flow that goes like this, because that means I would have a pressure gradient that would go like this. I would have a jump somewhere, but I don't, which means that the pressure gradient has to be the same everywhere. So the third law, no, the zeroth law of thermodynamics is in place. Then the first law, cyclic processes. Now that's one of the places where you can really see that this had to do with thermodynamics and steam engines when thermodynamics was produced. But one can make an analog. So here is a flow going in this direction. These are all porous media. Sitting in the flow here with a flow rate QR, agitator theta R, and the saturation like this. And if I now follow, somewhere goes out here, but somewhere goes in here, and then this gets narrower, so it gets heated up. And this is adiabatic. And here it meets another flow, which in this case here, L is slower. So then they go here, and then you get back here, it expands. So you have adiabatic cooling, adiabatic heating, slow mixing, and fast mixing. This is faster than this. Gibbs relation. And I can actually write it down like this. This is the diagram for that process I just gave you. So this is adiabatic cooling, slow mixing, adiabatic heating, fast mixing. I don't change this one, which means that as a relation between the change here in the heat input into the system, and here is the work done. And what is the work? Well, that's a transfer of saturation from up here to here. So you actually, this is very complicated to analyze, but this is how you would go about it. All right, a second law of thermodynamics, pseudo-thermodynamics here is I inject here, and you see here, here's a dark liquid coming in, here's a white liquid coming in, and up here you don't see this anymore. So you have here an non-equilibrium situation going into equilibrium, and that means that the entropy is increasing and then reaches a maximum. This is the second law. The entropy is fixed or increases. Closed systems. All right. So now we're getting to the cone-moving velocity. So now actually, this is a talk I wrote the abstract for. Okay, so here were the thermodynamic velocities as defined in this pseudo-thermodynamic. But this is not what you are measuring experimentally. What you measure experimentally is you have your porous medium, you send the two liquids in, and what you do on the other side is have buckets, and you see how much of this liquid or that liquid ends up in the bucket per second, or per hour, actually. So these are very different things. But it turns out that there's a connection between them, between this seepage velocity that you measure directly and this thermodynamic velocity that you measure indirectly. Namely, this velocity here is this velocity minus the non-wetting saturation times a function Vm. And the same thing with this velocity you measure directly is the thermodynamic velocity plus this wetting saturation times this function Vm. And this is the cone-moving velocity. And it turns out this sits outside ordinary thermodynamics. You don't find an analog in ordinary thermodynamics. This is something new. It needs its own equation of state. But I'll get to that. Here's another way of seeing the same thing. I have a wetting liquid velocity, and I have a non-wetting velocity. These are without the hats, these are the measured ones. And then you have an average velocity. If you measure the average velocity, can you reconstruct the two velocities? And of course, the answer is no, because there's no unique way of splitting. Right, I have one relation, can I split that into two relations? No, I need a second relation. And that second relation you can get if you introduce the common velocity. Which means here is the wetting velocity, here's the non-wetting velocity measured, and here's the average velocity, here's the common velocity, and this you can go both ways. So you combine constitutive equations for Vp and Vm to transform and get these two. And why would that be interesting? Well, it turns out that this Vp here, you know, we have the nice regime where the relative permeability works quite well, but there are other regimes where you have nonlinearities and horrible things. Now I sound like Trump, sorry. And you would measure this one here. How on earth could you reconstruct these? Well, as I said, common velocity is the thing. And this is how it actually ends up looking. So you start out with this is the average velocity. That's the saturation weighted average. You take the derivative with respect to the saturation. Well, if I take the respect VDS, I get VW, that's that one, and I get minus Vn, this is this one, but then I get the derivatives with respect to the velocities, each velocity itself, which is this part here. This here turns out to be the common velocity. It's not trivial. And then if I just plug that back in here, I have now the common velocity, another expression for it. It looks like this. And here's a two-way mapping. Here's the average velocity, and here's the common velocity. You see the difference between the average here and the common is that I have to take the derivative of this one and this one. That's it. And I can now invert this, and I have here the two velocities of each, the velocity of each liquid, given in terms of the average velocity and the common velocity. So constitutive equations for Vp and Vm give constitutive equations for Vw and Vn, which is very nice when you're dealing with nonlinearities. Okay, so let's look at what it looks, let's find it. What does it look like? So let's use the relative permeability data. This is work done with Subadip-Roy here and Sant'Anasina. So here's the common velocity. Here is the two relative permeability equations, and what people do is they give you the relative permeability. So the literature is full of the measurements of this. So what we need to do is to get these two here into this one here. So what we do is I just pick out this core here, which is just the wetting velocity if the saturation is 1. So this is V0. Then I can write down the average velocity like this. M here is the viscosity ratio, and here's the common velocity. And then you go into the literature, you simply find Vp as a function of saturation. In the literature, using relative permeability data, these are two types of data sets. Here is the common velocity now in the function of saturation, but here it is as a function of the flow derivative, Vp, dVp ds. Here's another measurement, another set of data. Look, the average co-moving in terms of S and co-moving in terms of the flow derivative. Here's another set. This was not wonderful, but some data are good and some are not. In terms of being nice to look at. See, like this. Here's another set. Here's another set. Here's another set. And the criterion we used to choose data sets were to have no criterion at all, because, you know, you can't start having preconception of what you want to find. So it looks like Vm is a constant plus another constant times this derivative. And that was actually predicted, I mean, that this would be the good variable, natural variable. That comes from the statistical mechanics, actually, because, yeah, I don't want to get into that. But anyway, and this is data that were analyzed by Stefan Berg at Shell in Amsterdam in January, actually. So he took different relative permeability data sets from their big stock, and he found this one, he found this one, he found this one, this one, this one, this one, this one, this one, and it all added up to 43, and all of them were this kind of quality. So it really looks like a straight line. Oop, I turned off the screen. And here is dynamic for network model data. This is work by Subali and Santanisinho. And you see also the absolutely gorgeous straight lines. And these are the two coefficients. They depend on the pressure gradient, which you wouldn't expect because they depend on the agitator. This is exactly what they should do. And the consequence as well, you have that the two velocities for each liquid. Here's the relation I had before, and this is what it looks like. So it's just two coefficients here. Otherwise, you get everything from this average velocity. Here is some work with the people in Australia and the US. Here are the relative permeability data for North Sea sandstone, Bentheimer, and experimental data here. And this is liquids with different. The only thing you change is the wetting angle. And here is the average velocity and the different wetting angles here. Here is the common velocity, and you change the as a function of saturation, and you see you get this bundle. But if I plot it in the right variable, well, it ends up being straight lines. Here's another data set, same thing, straight lines. Here's the experimental curves. You see not much overlap here, but it ends up being looking like this. So, I mean, I have little doubt that there's straight lines here. So what can I do with this? Well, solution to these equations, it has solutions. This is one, relative permeability. This is another solution of this equation. So you actually have an equation here that can give you relative permeabilities that are okay and those who are not. Before, they have always been treated as completely independent, measured completely independently, and you do the best fit you can. But now you actually have an equation for that thing. All right, and you can then actually go further. Knowing one relative permeabilities, you can find the other one. If you can measure one with very high precision, you get the other one. And this is kind of data. I'm not going to go into details here. But let me now, since I have a few minutes left, water ethanol mixture. Now go into real thermodynamics, classic thermodynamics. Forget about porous media. So I have water and I have alcohol, I mix the two. And here is the volume of the mixture as a function of percentage of ethanol. You see it goes from 1 liter down to a minimum here, 0.965, and then up again. I start off with the Gibbs free energy. Take the derivative with respect to the pressure, I get the volume, and the volume. Then I can write like this. This is in all textbooks on thermodynamics of mixtures. So I have a V1 here and V2 hat. These are volumes now, and these are the thermodynamic volumes. This is called partial volumes. This is with the number of molecules type 1 and number of molecules of type 2, or moles type 1 and type 2. You get this one. But I can also go in, use molecular dynamics and measure actually the volumes associated with each of them. And I use the Voronoi tessellation here. So these are then particles of type 1 and particles of type 2, and I do this area here. This is the area belonging to this particle here, and I can just add up the two, and that gives me 2 volumes. These are now the Voronoi volumes. Is there a relation between the two? Well, and they have exactly the same form. You see this equation here and this equation here have the same form. Like this. And I go into this relative variables. Xn is degree of concentration of one of the liquids. I have this relation. And then I get a co-molar volume. This I call the moving velocity when it had to do velocities. Now it's a co-molar volume. And what do you find when you do the molecular dynamics? Well, this is a master student. He's doing his master thesis right now. And this is his preliminary data. And damn it, it's a straight line. It's a straight line. Which means that the straight line you see for the co-molar velocity has nothing to do with this being porous medium problem. It's in the mathematics. It's in the mathematical structure. But you can see at the same time, it's not part of ordinary thermodynamics because you don't have this kind of directly measured quantities there. So this is actually an extension. Where does this come from? Well, you can do a dimensional analysis here. The 2 parameters is A plus B times this V derivative. And you see I divide by V0 here and divide by V0 here. I've written it down. You can see what this is. This is actually an Euler homogeneous function of the first order. Take the derivative with V0 and set V0 equal to 1. And I have this form here. And this is a function. It has to be a function of, I have only one choice, and that's a function of this. And this thing here is a function of like this here. I cannot do it in any other way. And if I take the derivative of this thing here with respect to VP derivative, and I take the derivative of this with respect to A, I can switch them that we equal. This is a Maxwell relation. So I have a Maxwell relation here. I use it, and that gives me a relation between this F and a B. And then the next thing, and here I have to be unclear because I'm not 100% there in any ways. But what I'm going to say now is if you can find a solution to this equation here, and if you demand that this equation, the solution are not crazy, go to infinity or something, you have only one choice, namely this being constants. So this is 0 plus 0 is 0, and that gives you this.
So if there are questions, comments, yeah.
That since you are pumping 2 liquids, so is it possible that one of the liquids will flow faster and cut off, the path of another one penetrating because it is a disordered system? So does it form a pond sort of a thing, a lake, where it cannot penetrate any further? Your simulations of the 3D didn't show any of such pockets.
No, but that is certainly true. You would, this is a 2-dimensional system, and you don't see that here. Well, actually, if you do the statistics around this, Marcel has done that. You can see that there are preferred paths. It's a very structured system. And what you see, if you now go down with the saturation, at some point, one of the liquids is going to freeze and stop, and then you go through a phase transition. And the interesting thing is if you go towards, have the wetting liquid freezing, I think it's that one, you will see a jump. That's a hysteresis. But if you go the other way, the non-wetting liquid, when that stops, there's no hysteresis. So it seems to me to be something like a second order transition on one side and a first order in the other side. And when I talk to people who are engineers working in this field, the first thing they say, can you do hysteresis? And I tell them, physics is full of hysteresis. The Maxwell construction in the 1870s was actually set up for this. Yes, we can do that. Hysteresis, I think, comes from this kind of phase transitions happening.
Hmm.
the question. So, so is it possible that, one liquid is moving in, and since the other liquid is moving, and presumably they have two different viscosities, could one penetrate into the other to form viscous fingers?
Yes, they could, but remember this is steady state. So what you actually see in practice, if you have a cluster, you will have on one side you have viscous fingers coming out, on the other side you will see imbibition. But these things, when you actually look at this in practice, you will see these clusters and they break up and then they merge and so forth. You really can see the difference between them. So viscous fingers.
You won't be able to see them at the macro scale.
No, you wouldn't be able to. And also, if you look at it carefully, I mean, because the system is too intermingled.
Right.
So when you're dealing with steady state, I don't think you can really distinguish between them.
You have not taken that.
Yeah, no, it's not a good concept.
All right. Well, these have been there.
Any more questions, comments? Just one. I mean, in all these cases, I mean, since basically Darcy's law is there, so if I increase the pressure gradient, even for a single fluid, I mean, there should be extra order pressure gradient. I mean, del P square, del Q, and these are. I mean, don't you see that or?
Yes, we do. I mean, Oslo group was the first to see this. The Oslo group saw this in 2009. What they measured was essentially flow rate as a function of pressure, or rather pressure gradient, pressure drop across the system as a function of flow rate. And what they found was that the flow rate goes like the pressure gradient squared. And the reason for that is as you increase the pressure drop or the flow rate, you are mobilizing more and more interfaces, which means that your effective viscosity, effective permeability goes up, and when you integrate that, you get the flow rate. So that is that exponent plus 1, and it turns out to be around 2.
This for the P square, delta P square term.
Yeah, well, it turns out.
What is the prefactor? I mean, you had K and mu. I mean, in this Darcy.
Yeah.
I mean, what prefactor? I mean, just dimensionally, what are the prefactor?
What you find is V is minus, and you set up a mobility as a function of saturation. And then you have dP, and then the exponent to minus 1 times dP. This would be the equivalent of the Darcy. Where this usually, I mean, that usually is K over phi mu, but here it would be something else, because
I mean, beta is
that part really hasn't been explored much. But it really is very, very interesting, this, because if you now do pressure gradient here and flow rate, and you take log, you find this, and then suddenly switches over and then switches back again. This is when you have a channel so open that actually allows flow, and you're not mobilizing any interfaces. And then suddenly you go into this critical region where you're mobilizing more and more interfaces. It's just like if you have a granite packing and you're pushing it more and more and more, then more and more grains come in contact, and you see this thickening network. You see exactly the same thing here. And this is, it goes back to linear, because now all the interfaces are moving. And this region here, which is actually quite important, because this is when the viscous forces and the capillary forces are in competition, and they very often are in real processes. That is when relative variability goes bonkers. You can't do it. I mean, cannot handle this. No way. Cannot. Yeah.
Which would be let's just keep it up and loud. And with the two lines, the initial slope and the terminal slope, pass to 0.
Depends if the system is percolating, it passes through 0. If it is not percolating, that means you have interfaces that block, you have a threshold pressure. Typically Q, but then if it passes, it would be, it would be something like this. And then otherwise it would end up down here. Sorry. It would be here. This would be a delta PC. Threshold pressure.
What's your final?
Yeah, the final part of it, it goes back in. That is when it goes back linear. Because that's where all the interfaces are just moving along. You know. Yeah.
Okay, Dr. DS one. Yeah. Okay, brief one.
Darcy's law.
Okay, so
Could you have solved for the Navier-Stokes equation and found out the velocity at every point, numerically? Because this is like the pores are so microscopic, and Darcy's law is more at a macro level. So, do you think that would be better?
The way we have used this now is that we have used statistical mechanics to sort of put meat on this pseudo-thermodynamics, and we've been working only on that one.
You would have thought still all your values.
But you see, I have never in this talk here talked about something like what would be a Hamiltonian-like thing. There's an underlying symplectic structure here, by the way. But we haven't been able to find a good model.
But you could have still found the velocity at every point for a given pressure, and taking into account your viscosity, your everything. I mean, body force.
This is what some of the data I showed is on, part of it is done real experiments, but part of it is halfway experiments, in that you reconstruct the porous medium completely, and then you put a lattice Boltzmann calculation on top of it. That means you have all the velocities, everything. Yeah.
okay, if no more questions on this, then let us thank the speaker for an excellent presentation in this.